All right, we're back. People are wandering back in the room. So we're going to head into the fourth quarter, and it's going to be kind of it's going to be a little bit of a grind in a good way. And to kick it off, we have another back-end compiler developer, one of the lead developers on the back-end compiler of Visual C++, Eric Brumer.
So yeah, my name's Eric. I've been working on the compiler optimizer for 6 years now, mostly auto vectorization related. This talk's going to be a little different than the others, so I just want to say that up front. We're going to be going into some of the internals of the compiler backend, sort of things you may not have known, things you might not want to actually know of how we actually generate code. So let's get started. When you think compiler, I think front-end errors, I think front-end warnings. I heard a really interesting thing about what the compiler is. The compiler is that thing that puts your destructors in the right place. Okay, it does that, sure. But look, you're writing your code. There's a lot of code generation and optimization that goes on to get your code to run as fast as possible on that thing, and on that thing. There's a lot of extra stuff that goes on behind the scenes after you've fixed your errors and ignored your warnings. We're native code folks. We care about performance. I hope every single person here, to some measure, really cares about the performance of the code that they're writing. And the compiler optimizer just has a lot of say in that. There's a lot to do for optimization in that, to say about optimization for that. So for this talk, I really want to expose some of the guts in the optimizer. It's going to be a pretty low-level talk. It's going to be a little bit different than what the past talks have been. There's going to be raw loops, Sean. There's going to be assembly code. There's going to be microarchitecture diagrams. It's necessary, though, or at least I think it's necessary, to talk about some of the compiler optimizations from the point of view of the hardware. We really need to go into these assembly code microarchitecture type things. So I want to talk initially about what modern processors actually are and how we can eke more performance out of it from the compiler's point of view. And then I want to give two optimizations that sort of take advantage of that kind of stuff. One's vectorizer and one's this indirect call optimization thing. So let's just get right into it. So you may have seen this diagram before. Right on the left-hand side, we've got a Pentium chip, 3.1 million transistors. It's the processor of yesteryear. On the right-hand side, there's Intel's Haswell processor. It's got 1.4 billion transistors. There's sort of a lot of stuff in that. This diagram is not to scale. If we took the Intel design and printed it on modern transistor technology, it would look a little bit something like this. That's a little bit more accurate representative of what Haswell is compared to what the Pentium chip is. And basically, it comes down to there's just a lot of silicon. There's a lot of transistors. There's a lot of money put into the design of these chips. And on the compiler side, we absolutely have to take advantage of it. That's the only way to get the performance that we're all craving out of these modern processors. One of those things that's been added since the older Pentium chips has been the vector hardware, the compiler optimization. I'm just going to give a very, very brief explanation of what automatic vectorization actually is. We're going to use this later in the talk. I just want to give a very, very quick overview. So basically, automatic vectorization takes your existing C++ code and compiles it such that it uses the vector instructions. We make use of that right now to execute multiple loop iterations at the same time. This is easiest to be explained through a small example. This is a raw loop. Sorry, I don't mean to be that guy, but I kind of am that guy. So this is a loop. I've got an induction variable I. It goes from 0 to 1,000. We're just doing a sub I equals b sub I multiplied by c sub I. And let's just say that a, b, and c are floating point arrays. They're floats. They're 32 bits. And if you look at what actually happens on each iteration of the loop, they're 32-bit operations. It's a 32-bit load of b sub I. It's a 32-bit load of c sub I. It's a 32-bit multiply and a 32-bit store of a sub I. So what does it mean to vectorize this? It means to turn the code into something that looks a little bit more like this. So instead of doing 32-bit operations, we're doing 128-bit operation. Specifically, it's not 128 bits, it's really 4 times 32 bits. So instead of loading one value from b sub I, we're really loading, and I like this kind of weird syntax for it, b sub I through I plus 3. We're loading 4 32-bit elements from b. Similarly, we're loading 128 bits from c sub I. We're doing a packed multiply. That's that mul ps instruction. It's just the vector instruction that the chip has nowadays. The goal of this is that we can get speed up because the loop only has to iterate 250 times. The real speed up comes from all that extra silicon that's available. This 128-bit multiply takes exactly the same amount of time on the hardware to execute as a 32-bit multiply. Just want to say that one more time so it sinks in. You can do 4 32-bit multiplies with one instruction in the exact same amount of time that it takes to do a single 32-bit multiply. That's sort of the key point that sometimes gets lost when you're talking about vectorization. All right, this is the first of many times we're going to see this picture. So, it's the microarchitecture diagram that I warned you about earlier. Specifically, this is the microarchitecture diagram for a Haswell core, a single Haswell core. On the diagram I showed you before, there were 4 of these on a single die, soon to be 6 on a single die, I think. In the C++ compiler world, we talk generally about the front end and the back end. So the front end of the C++ compiler does, lexing, parsing, that kind of stuff. The back end does code generation and optimization. You can also think about CPU chips in terms of front end and back end as well. It's easier to explain what the back end is first. And that's basically the execution units on the chip. So when you think about modern processor power, if you go to any website where you're going to buy a processor and you look up any Intel or AMD chip, it's going to list, I've got this many vector units that can execute this vector instruction set. I've got this, I've got this, I've got this many adders and stuff. That's really what the execution units are. And in the case of Haswell, there are 8 pipelines in each core's backend. 8-wide superscalar. That means it can, at peak performance, it can execute 8 instructions in one single cycle. Right, so we're talking, a 2 gigahertz, 3 gigahertz chip. So those are the clock ticks. Every single cycle, you can potentially potentially ship off 8 instructions to the back end. So something to keep in mind. We're going to come back to that later. On the upper side, we've got the CPU's front end. The way I think about the front end is its job is to ship instructions to the back end, the execution units, as fast as possible. Noticeably, the way that's really done is with powerful branch prediction. And we'll get into more. We'll get into more of that later. But suffice it to say, I hope some of you guys have at least heard of branch prediction before. In general, most code is not as straight line as we all think it is. Even though you might write a bunch of code that looks like this, there really are a lot of branches. The last time I checked, 1 out of every 5 instructions that's executed by the processor is a branch. And at peak performance, when you can execute 8 instructions at a time, you're going to see at least 1 branch every cycle. That's on average. So being able to predict what those branches are actually going to do is absolutely critical to modern performance, or performance of native code on modern processors. We're going to get into that in some good detail later. So that's all hardware, sort of pretty low-level stuff. I want to now talk about some compiler optimizations. So what do I mean when I say vectorizing for modern CPUs? It just means we're going to take advantage of all that silicon that the chip has to offer. Remember, all that silicon that the chip has to offer. And one of the things we do is something I call conditional vectorization. I want to motivate this with an example. Look, conditional vectorization, we're going to vectorize a loop and guard the vector loop with runtime checks in the case of overlap. It takes 5 seconds to explain, but I want to go into some absurd depth into why we really need it. I think it's beneficial for folks to sort of understand where compiler optimizer guys are coming from. We sort of don't just make things up as we go along. There really is a lot of depth to the things that to some of the optimizations. So we're going to be spending a little bit of time on this code right here. It looks a lot like that last example that I just gave about vectorization. It's the same for loop. It's the same inside. A sub I equals B sub I times C sub I. Something to keep in mind is I am using C-style arrays here, float star A, float star B, float star C. Everything I'm saying applies directly. If you replaced float star with standard vector ref or standard vector star, it's exactly the same. That doesn't change. Don't be afraid. Oh my God, I'm a C programmer. It's okay. It still totally applies to modern C++ code, except if you're not using raw loops. So let's just go a little bit slowly and actually see what this loop is really doing. So let's say A, B, and C are pointing to distinct chunks of memory. I have the A's bar of memory is at the top, B's in the middle, C's on the bottom, and we've just got pointers to those pieces of memory. This is pretty straightforward, so you're going to see me start to talk pretty quickly, but hopefully this isn't too confusing. I'm pretty sure we can all sort of drive our way through a loop like this. I promise you I'm getting somewhere, though. So in the first iteration of the loop, we're going to be loading from B sub 0. We're going to be loading a float from C sub 0. We're going to do a 32-bit multiply, pack the result in A sub 0. Yes, good. We finished the first iteration. Second iteration, we're doing the same thing. We're loading B sub 1. We're loading C sub 1. Multiplying together, we're putting it in A sub 1. This is pretty easy to vectorize if I handed you a way to load 128 bits of memory in an instruction that did that packed multiply, that mul-ps instruction. Right, you just do 4 at a time. You load 4 elements from B, you load 4 elements from C, you do that packed multiply, you store it into A. Okay, this is not all that interesting. Where's the interesting part? The interesting part comes if there's overlap. So what if instead of 3 distinct chunks of memory, we just had 1? And those pointers are pointing to portions inside of that. So here I've got B pointing to the beginning, I've got C pointing to this third element, and I've got A pointing to the fifth element. And I will state this again, if you replace the float star with std vector ref or std vector star or whatever, you can still have the situation. You can initialize a std vector by giving it a floating point pointer. So this totally applies to C++ code as well. Okay, now I want to start running this code again. And I'm going to start by doing it 1 iteration at a time, and you're going to sort of see where things get a little confusing. So the first iteration of the loop, you load from B sub 0. That's at the beginning of the array. Then you load C sub 0. So the next element also happens to be the same thing as B sub 2. You do the multiplying, you store it into A sub 0. Okay, great. The next one, you're loading B sub 1, you're loading C sub 1, and you're going to store it into A sub 1. And A sub 1 also happens to be the same thing as C sub 2, kind of interesting. The next thing, we're loading B sub 2, we're loading C sub 2, and we're going to multiply those and store it into A sub 2. Okay, here's an issue. A sub 0 feeds C sub 2. So we just loaded on the third iteration of the loop from C sub 2, that one chunk of memory, that vertical red bar right there. But on the first iteration of the loop, we wrote to that particular spot in the loop. And this right here causes the vectorizer to go a little bit crazy. So the easiest way to do that is what happens if we actually try to naively vectorize this? What happens if we actually try and do this 4 iterations at a time? We would load the first 4 elements from B. We would load the first 4 elements of C, and already we've got a problem. We are already loaded C sub 2, but we haven't yet written to A sub 0 yet. You're going to get a different answer if you naively vectorize this loop. That's all I'm really trying to say. Is that clear? I hope it's clear. Should be pretty clear. Good. One way of saying this is that the presence of overlaps prohibits vectorization. Anyone here? Have you actually ever written some code where pointers actually overlap, where arrays actually overlap? And here's the thing, the law of large numbers tells me there's going to be 5 people in this room that actually do it. I count 1, 2, 3, 4, 5, 6, 7. Okay, it's pretty close actually. Now everyone's raising their hand. Yeah, thanks. But look, most of the time, arrays really don't overlap, right? They could, but for the most of the time, they don't. So I don't like that statement. I'd rather much say the presence of possible overlap prohibits vectorization. That one single word changes the landscape a little bit. The compiler's still able to generate fast code, and this is how we do it. We've got this situation. So at the top is the same source code we've been looking at for a little while. The bottom looks a little bit different now. It looks a little bit bigger, for one. So we emit the naively vectorized loop that 4 iterations at a time. We also emit a duplicate version of the loop that is not vectorized. We then guard that vectorized loop with runtime checks that actually check, does A overlap with B? Does A overlap with C in the context of the loop? In this case, the range from A sub 0 to A sub 999, does that overlap with B sub 0 through B sub 999, stuff like that? So you might seem okay just sort of to stop there and say, hey, this is what we do. This is the kind of optimization that we do. But I like to sort of take it all the way to the end and really talk about the performance, like the really nitty-gritty stuff about compiler optimizations. I really like that, and I hope going through it's going to be somewhat like enlightening. So what we've emitted, you wrote that loop. You wrote that one a sub I equals b sub I times c sub I loop. We are actually generating a vector version of that loop, a scalar version of that loop, and 2 runtime checks. Each runtime check has a compare instruction and a branch instruction, so it's 4 extra instructions of runtime checks. The code size of this increases by 7-fold. That's big. Yeah, that is big. Now, granted, a loop of this size overall is actually a small amount of assembly, so increasing it by 7-fold really isn't that much. But still, it's important to know that it's 7-fold. Speeds up, though, the whole thing. Of course, if there is no overlap. If there is overlap, there couldn't be any speed up. That would make no sense. But right, most of the time there is no overlap. And we get a 2.63x speed up. It runs 2.63 times faster. First question that I'm sure most of you are thinking at this point, well, what if you just vectorized it blindly and you didn't have to duplicate the loop and you didn't have to insert the runtime checks? Right? What if the compiler was actually able to prove that the arrays didn't overlap? What would the speed up be then? Any guesses? Right? If we actually took the original source code and vectorized it without duplicating the loop and without inserting the runtime checks. Any guesses how much faster? Ooh. Chip, I heard Chip say 2.64, and he hasn't seen my slides before. It is 2.64, and you knew that because I put the speed up to 2 significant digits. So, I'm just going to say this again. If we vectorize this and didn't insert the runtime checks and didn't insert the duplicate loop body, we get almost the same speed up as if we actually have the runtime checks. The processor is so good at executing those 4 runtime checks every single time, before the loop body executes, that it makes no difference at all, basically no difference at all to the end performance. Kind of interesting. Question? What's up?
2 questions. What's the change to the code size?
Almost nothing. It goes up by just a little bit. The vector instructions aren't that much bigger than the scalar instructions.
The other question was what's the performance impact when you run it on an architecture without vector support?
Okay, so yeah, let me just repeat the first question for folks listening online. So what would the code size be? I've got my scalar loop without vectorization. That's this over here. And then I've got my loop that's got the vectorization but doesn't have the duplicate and doesn't have the runtime checks over here. How much bigger is this versus this? And it's not that much bigger, right? The vector instructions are almost the same size. They're just a little bit bigger than the scalar instructions. That could change if we decide to unroll more aggressively or less aggressively. And our compiler does make those decisions based on vectorized versus not. Yes. Yeah, it's huge.
So what I'm saying is, how much does that 7x go down if you don't have the duplicate loop?
If you don't have the duplicate loop, that 7x goes to 1.05. Let's guess. Yes.
Okay.
Yes.
So there's not a difference in runtime speed for vectorization with runtime check and without the runtime check.
That's right. There is not.
Like a 7x difference in code size.
Yes, that's absolutely right. So there is no runtime performance difference if you're talking about duplicating the loop in the runtime checks, but there absolutely is a code size difference. Absolutely. That's right. Guys, I've got a lot more. We'll take some questions in a little bit. Yes, and so why is this really the case? And it's all that extra silicon that's available. Yes, the code size is absolutely important, but for now, and just now, I am focused largely on the performance of code. However, for every single optimization I give, I will be describing what the code size increase or decrease is going to be. Okay, I've got another example of this conditional vectorization. This one's sort of taking it to the extreme. This is some code. That's a loop, so basically everything that you see is a whole loop body. This is code from a spec industry benchmark that does DNA sequencing. And the loop is vectorizable only if you can ensure that none of those arrays in orange actually overlap, because this thing is written in C and it's using arrays, and every single one of those is an array. And in order to vectorize this, we have to emit 42 runtime checks, which turns into 82 compare instructions or 82 compare and branch instructions, not to mention the duplicate version of the loop. And in this case, the code size increases by 4x. Now, I really like talking about high-tech problems in terms of like low-tech demos. So I took that loop body that was vectorized and I printed out the assembly code on really small font, and it's like double column too. So don't worry if you can't read it. I can't read it, and I'm holding it right here. So This is the assembly code for just the vector loop that we emit. It takes one whole page of assembly. This is the assembly code for the duplicate scalar loop that we have, right? It's just a little bit smaller than the vector loop. We have 2 pages worth of runtime checks. 2 pages. This is absurd. This is just plain stupid, right? This makes no sense. Why would we ever do something like this? Because it's faster. So the loop itself goes twice as fast, and it just so happens in this case that this particular loop is a large part of the benchmark. The overall benchmark actually speeds up by 30%. And Chip, let me ask you this one again. So let's say we vectorize the loop, but we didn't need to insert those 2 pages worth of runtime checks. What would the speed up be in that situation? I don't mean to put you on the spot. I'll just give you the answer. 2.5. It's actually 2.1. So think about that for a second. We've got 2 pages of runtime checks. 2 pages. That's a lot of code. That's 84 instructions. And they're not like just straight line instructions. Every other instruction is a branch. But we're able to match the performance almost exactly to what you can get without even needing those runtime checks, in the first place. I think that's really cool. What is the value of M? Ooh. Of n. You mean what is the value of the loop? What's the loop bound? And it's the letter M. I copy and paste it, and it was M. I don't remember.
Number of layers, 1,000, 10,000. For speed up would depend on.
Geez, I don't remember. If someone's got an enlistment in the branch that I work in, I can find it for you. Ask me that question on the either afterwards. We'll look it up. No, that's a good point. But keep in mind. Look at what the loop body's doing, right? Even if M was only, say, 512, right, as opposed to 50,000, right? There's still a lot of stuff that's going on inside the loop, right? There's a control flow inside the loop too, right? The actual loop body, each individual loop body, spans multiple cache lines, accesses all sorts of data. I'm actually not sure that the upper bound of this loop matters too much if it's over 512. That's my guess, but I'll check up on that. It's a good question. Okay, enough with this vectorization stuff. Let's talk about something different. I call this indirect call optimizations, but the easiest way of looking at it is really through an example. So I've got some code here. I've got 2 functions, func1 and func2. Func1 just takes its parameter and returns a parameter plus 100. Func2 just takes its parameter, returns a parameter plus 200. And what really matters for me is this function called test that takes a function pointer, which is typedef at the top. I know. Typedefs and function pointers. Geez, what am I thinking? At a C++ conference using typedefs and using function pointers. But anyways, this is the example that I want to use. So we've got test, which just calls through that function pointer and passes the parameter 3. Seemingly simple. This is the assembly code that we generate for test. This is what any self-respecting compiler, just with the information that it's got, this is what it's going to be generating. Load f, your parameter, into some register. You're going to push the argument 3 before you make the call. And when you make the call, you're going to call through whatever you loaded from f. In this case, I'm just using the ECX register just because. And just to reinforce this, when the call instruction actually executes, it's going to take whatever 32-bit value it's loaded from f and set that to be the next instruction that we're going to execute, just to make sure it's an actual transfer of control flow. I don't really know how else to say this, but this particular set of code gen, those 3 instructions are terrible. They're miserable on modern hardware. And I want to really talk about why, and I'll go into some really sort of gritty detail about why that's actually the case. Here's our microarchitectural diagram again. So I'm looking at this particular set of instructions on Haswell, but this really does apply to most modern processors, even on ARM. Our ARM stuff as well suffers from this issue. So I've got my 3 instructions at the top left, right? The load from F into a register, the push, and then the call from whatever we've loaded. And let's say they all exist on the same cache line. So in one cycle, they all get loaded. In one cycle, they all get decoded. And the scheduler is able to understand, hey, this is really a move instruction. This is really a push. This is really a call. Then, then the scheduler takes over. And this is the scheduler that can actually dispatch 8 instructions every cycle. So it looks at all of these at the same time. And it says, hey, who's ready to execute? And it realizes the first instruction loads from F. OK, let's start executing that. And at the same time, it realizes the push has nothing to do with that move. So it goes ahead and it executes both of those 2 instructions. It ships it off to the back end of the processor. What about this call? Can't execute this call yet because we haven't yet loaded from F. This seems trivial. Yes, of course you haven't loaded from F. So what? You load from F and then you call. It's not that straightforward. So if you're lucky, if you're really, really lucky, the value of F exists somewhere on the chip that's really, really close to the execution units. If you're really, really lucky, it's in a store buffer somewhere. And then it's only going to take like 2 or 3 cycles for you to get the data from F into ECX, which is then going to actually figure out, hey, this is where I need to actually transfer my execution. This is the next instruction that I actually need to execute, or the address of the next instruction that I actually need to execute. If you're less lucky, F isn't in your first level cache, it's not in your store buffers. Let's say F is in your second level cache. You're talking 12 to 15 cycles before you actually get the value of F inside ECX, which you can then forward to the call instruction to actually find out what the next instruction is going to be to start executing. That's 12 to 15 cycles on a chip that can execute 8 instructions every single cycle. We've got all this silicon, all of these transistors available to us, and we're just not going to use them if F is in the second level cache. And you know what? That actually happens a lot in this type of code. What the hell, right? You know, this chip is so powerful, it can execute 8 instructions every single cycle, and it's just going to sit there for 12 cycles. You can do a square root of a 32-bit number in 12 cycles using one core. This whole chip can do your math homework in the time that it takes F to go from the second level cache onto chip, so you can actually figure out what next instruction you want to execute. I need a minute. This code gen really bothers me. It's painful. Okay, I want to fix this. So what I'm going to do now is rewrite my function test, which I really don't like the code gen, so we're going to rewrite it to something better. And I'm going to change it to this. So I'm first going to check if F, the passed-in thing, is equal to func1, and if so, I'm just going to call func1 directly with parameter 3. And if F is func2, just call func2 directly with the parameter 3. And you know what? Hey, I consider myself a decent programmer. Let's say someone in the future is going to write a func3 or func4 or func5, right? My code is future-proof. That's OK. This is the assembly code that we now generate for test. It's bigger, a lot bigger. And this is starting to look a little bit more like confusing assembly code, so let's just walk through it very, very, very quickly. At the beginning, we've got the same move from F into ECX. We've got the same push, so we're going to push the same argument to whatever function we're about to call. And then we compare whatever was loaded from F with the address of func1, and if it actually is func1, we call func1. If not, check func2. And at the very bottom, we've got our old code, to call through whatever F was originally. That jump right there, that's guarding that direct call to func1, is really important. All right, I want to explain why by going through the same exercise with all these instructions on the same microarchitecture diagram. So let's say we've got our first 5 instructions. They all exist in the same cache line. They can all be loaded at the same time. They can all be decoded in one cycle, and the scheduler is able to interpret all the instructions and figure out what's ready to execute. And just like before, the first 2 instructions, the load from F and the actual push, they can be sent off right away to the execution units. And similar to before, we still have a stall on that compare, right? The compare is comparing the value of F to something, but we haven't loaded the value of F yet, right? That compare might actually have to stall for the same 12 to 15 cycles that our old call had to. The fun part comes is we can predict if this branch is taken or not. We can leverage what the hardware developers have done in terms of branch prediction. You're talking like 90-ish% accuracy in terms of being able to predict this branch. Let's just say we predict this branch is actually not taken. Let's just say we predict that the value of ECX really is func1. We go ahead and we speculatively execute this call instruction. Now what's nice about that is we know what we're calling. We're calling func1. The address of func1 is built into that instruction. We just go ahead and start executing. Now, of course, if the predictor actually predicts wrong, the processor needs to, it's called squash all those speculative instructions. That does still need to happen. But what if it guesses right? And it does guess right 90% of the time. Once the value of F actually comes back onto the chip, you've speculatively executed all these instructions. You just let them commit. It's really cool. I think it's really cool. I'm pretty excited about this. This is so much better than the last code gen. It's just night and day. And of course, I really, so I want to explain, just again, just to make sure this sinks in. It's same source code, same assembly that we've been dealing with. I just want to explain what the differences are here. So the code on the left is one version of the code. The code on the right is another version, and the assembly code is right below it. On the left, we stall because we don't actually know where we are transferring execution. The code on the right, we are not stalling. We are entering speculative execution mode, and we're taking advantage of the branch predictor. So we're turning an indirect function call into a direct function call that's going to be speculatively executed based on a branch prediction of a branch that's actually guarding it. And this does make the code go faster. We're going to get into some details in the next slide for that. But of course, I'm a compiler guy. I haven't said anything about a compiler yet, right? I've just actually rewritten this code, add the if statements by hand. But the compiler can do it for you if it's got the right profile information. We'll talk about the profile information in just a little bit. But let's just say we have this profile stuff around, and the compiler is actually able to know stuff about your program. So I got the same source code, the original source code that generates the really bad assembly that's on the left. So what if the profile counts say that when we're executing tests, we're calling func1 around as often as we're calling func2? The compiler will insert those checks for you. Those same checks that we put in. If f is equal to func1, call func1 directly. If f is func2, yada, yada, yada. Code size increases. It does. We've established that by now. There's a 10% performance win. 10%. It's pretty good. That's nothing to like shake a stick at. If I'm working on my code, if I made my code run 10% faster, that's a big deal. So I don't want to like gawk at that it's just 10% because we're going to get better as we go. But 10% is still pretty good. If the profile accounts say the test is only, say, calling func1, or that it's calling func1 a lot more often than it's calling func2, it's only going to insert that check against func1. And that's the code generation that we emit. Code size increase is not as bad. It's only 3.4x. Oh, by the way, all the numbers that I'm giving are with the Visual Studio 2013 compiler. Everything is like totally reproducible. I try my best not to lie, but if you catch me saying something stupid, please, I'll be more than happy to fix this stuff. But for now, this is my best attempt at this. And if func1 is called more often than func2, the branch predictor doesn't have to work as hard. And we end up getting a 15% performance win. We're getting better. We're getting better. Anyone know what's coming next? There's room at the bottom for one extra piece. What happens? Take a guess, sir. If you are always calling func1. So one thing I haven't gone into detail yet, and we'll go into detail later, these are profile counts. So you've taken your source code, you've compiled it with special switches. I'll talk about that a bit later. I just don't want to distract from this. You run your code. All right, let me finish, and then I think I actually understand what you're really asking. So you run your code, and the profile counts tell you, hey, every single time you've called test, you're really calling func1. Does that actually mean there is no possible code path that you could ever call func2? Right? The compiler is not necessarily able to prove that in this particular case here. If the compiler is able to tell that func2 exists absolutely nowhere in your program, yeah, we'll do that just without even profile counts. We'll absolutely do stuff like that. But no, what I actually am interested in is what if the profile counts tell us that test calls func1 way more than func2, but we then decide to inline func1. That's what the code generation effectively looks like. It checks to see if f is equal to func1, just return the value, because we're able to inline it and figure out what's actually going on. That return is a very, very straightforward a transfer of instruction execution. We don't even have to call another function. And all that stuff happens speculatively. And if f really is func1 most of the time, yes, code size increase 2.7x. I was got to talk about the code size increase. We got a 30% performance win. It's 30%. It's 30. That's cool. Come on. All right. And all of this is compiler driven, given you've got the right kind of profile counts. We absolutely do speculative inlining type of stuff like this, where we take an indirect function call and we turn it into a direct function call. Now, I work on a pretty old code base, and half of it is written in C. So yes, I do write code that has function pointers. Law of large numbers. I'm expecting 5 people that work on code that uses function pointers. What do we got? Ooh, lots more than 5. Ooh, lots of people use function pointers. Maybe you know what's coming next. Let's fast forward to modern C++ code, just for a second. What if I've got something like this? So I've got a base class called base that defines a pure virtual function foo. Func doesn't need to be pure virtual, just it's a virtual base class. And then we've got class A, B, C that all inherit from base and define their own version of func. And surprise, surprise, those bodies of func look a lot similar to the last example that we had. And then I've got my function test, which looks a lot similar to the last test function we had, where we're calling x arrow foo, and x is of type base. And the C++ virtual inheritance thing generates this kind of assembly code, where we take x, we have to figure out its virtual function table, we find the right version of func to call, push the argument, and then actually call whatever we need to call. And surprise, surprise, this looks almost identical to calling through a function pointer. In fact, that's what the virtual function table really is. It's just a list of function pointers. So everything that applies, everything that I spoke about for the last 20 minutes, talking about turning indirect function calls into direct function calls, completely applies when we're talking about virtual calls as well. And you know, the fancy words, compiler-driven, speculative, devirtualization, and inlining, is a lot of words. But the basic idea is the function pointer case, you know, the previous case, the C-style case. The compiler is basically not guessing, but using profile information to make a strong determination that a function pointer is pointing to a specific function. In the virtual class base, we're talking about, the virtual base class case, we're talking about the compiler using profile information to figure out what type your parameter is. It's kind of cool. We're solving this 2 different problems in the same way. We really are doing speculative devirtualization. I think that's pretty cool. And we'll speculatively inline whatever we think is going to be right. And it's all based on profile data. All right, so I want to do a little recap here. Overall, any compiler really has to take advantage of all the silicon that's available. Right? We got 1.4 billion transistors that are on modern, the Haswell chip. There's shared memory. There's all sorts of shared L3 caches among all the cores. There's an amazing, amazing opportunity in the compiler space. We just have to take advantage of the silicon. And one of the ways we do it is guarding optimizations with runtime checks. And we do that right now with automatic vectorization. I would love to extend that to other optimizations as well. It's just that when you are able to vectorize a loop, there's a pretty dramatic impact to performance. So we've targeted the speculative or the conditional optimization stuff more towards the vectorizer. And if you're interested, go on MSDN and search for this QVec report thing. So very briefly, if you take some code and you compile it with turn on optimizations, and you compile it with the QVec report :1 switch, you're going to get a list of all the loops that we have automatically vectorized. If you throw the /QVec report :2 switch, you're going to get all the loops that we vectorized, plus all of the loops that we didn't vectorize with a little reason code that explains why. So you're going to get a message like, loop on this line was not vectorized due to reason 1305. Now, I know that whole reason code thing is a little weird, and when you're using it for the first time, you're like, what the hell does reason 1305 mean? That means absolutely nothing to me. I wrote all those, and what I really wanted people to do was to actually go to MSDN and actually look up what the error code was, because I've got pages and pages of documentation that explain each error code and what you can do to try and fix it. Specifically, error codes that begin, or the message codes that begin with 15, so like 1501, 1502, all of those have to do with the pointer disambiguation runtime check stuff. So you're going to get messages like, we did not vectorize this loop because it needed runtime checks, but the runtime checks were too complicated to add. Or we could not vectorize this loop because it needed runtime checks, and we thought that the runtime checks were not going to be worth the performance win. Stuff like that. So those are kind of interesting, and those are all on MSDN. Yeah, I thought about putting the QVec report :2, could not vectorize this loop because we couldn't prove your upper bound doesn't change within every iteration of the loop, and that prevents that. And just sort of, you can't distill like 2-3 years worth of compiler work into a one-line error message. So I'd intentionally made these 4-digit codes that you have to look up MSDN, and I think there's an interesting dialogue that comes along with that. Anyways, that's a small rant. Yes, of course, the profile counts that I mentioned, specific to Visual Studio, the Visual C++ compiler, is profile-guided optimizations. So we've got all sorts of blog posts that explain what we do with Pogo, how Pogo works. Basically, you compile your code with an instrument flag. It generates an instrumented version of the binary that computes stuff, or counts stuff. It counts things like indirect function calls, virtual function calls, what things were actually typed appropriately, or what were the types of certain things at certain points of the program. It counts what code is hot, what code is cold, what data is hot, what data is cold, and then when you compile your code again with those profile counts as input, you get sort of better optimizations. And just using Pogo stuff, you can get pretty radical performance wins, like, again, between 10 and 30% sort of across the board for CPU stuff. It also reduces the working set workloads because it takes all your cold data, so data that you don't access very often, and puts it in one portion of the binary, and it packs all your hot data together so you access fewer pages of memory in the long run. It's really cool stuff. And no talk about performance would be complete without mentioning profiling tools. If there's anything that anyone could ever take away from any kind of performance talk, is you have to profile all the time, always. I recommend, if you're on Windows, the Visual Studio Profiler. You'll find out in a very pretty format what part of your code is hot. And that's where you're going to start beginning your investigation. If you're interested in learning things, how many times did this branch predictor guess wrong on this particular branch? Or how much data should have been in the L2 cache when it wasn't? And what kind of performance hit would this actually cause? Or how much performance win would I get if I made my data set just a little bit smaller so everything all of a sudden fit in the L3 cache? You're going to need to go to the hardware vendors' performance analysis stuff for that. So that's Intel VTune Amplifier XE and AMD's Code XL are two good programs for Intel chips and AMD chips. I like putting these links up at talks. So we've got all our compilers, switches, interesting things that you could look up there. Maybe there's things that you don't know about that can actually give interesting performance wins. If we, STL mentioned before that we should get rid of 32-bit cogen. I would love to get rid of 32-bit cogen. But in the meantime, yes, thank you. In the meantime, 32-bit cogen, you basically have 4 general purpose registers, sometimes 5, sometimes 6 if you're lucky. You can up that to 7 or 5, sometimes 6, sometimes 7 if you're lucky, with a special set of switches that I don't want to talk about because that's going to start a flame war. It's the frame pointer omission stuff, which some people think is good, some people think is bad. Depends what you're looking for. I don't want to get into it. We've got a cookbook and a series of blog posts for automatic vectorization that's on the native concurrency blog. Jim Hogg has been, he's the program manager on the optimizer team. He has been doing a great job, all sorts of interesting blog posts. We've got stuff on the Visual C++ blog as well as on the native concurrency blog. And then shout out to Charles and Channel 9 GoingNative. There are some really, really, really cool talks. I hope you guys know about it. STL has a whole bunch of series of talks on GoingNative, on using STL, using all sorts of cool stuff. There's also some performance-specific things there. There's talks on Pogo. There's talks on different kinds of optimizations, and so on. So I've got some time for questions. I do have like 15 or 16 minutes. I'm happy to answer questions for 15 or 16 minutes, unless you guys want to have just a little bit of fun. Just a little bit. I'll take your questions. I know your hand's been up for a little while. I'll get to you first. So I've got some backup slides just to give you a sense of what we have to do with the runtime checks. So yes, the title of this part of the talk is called Wild and Crazy Runtime Checks. I like that name. So our loop body is a little bit simpler here. It's just a sub I equals b sub I times 2. The times 2 doesn't really mean anything. It's just that if we wrote a sub I equals b sub I, we don't vectorize that loop. If you try to run this code at home, we're going to say loop was not vectorized due to reason code 1206, whatever. And you look up 1206 and it says, oh yeah, we're not vectorizing because you're just really doing a memcopy. And hopefully the code generator just ends up calling memcopy for you. But what I really want to get at is what actual runtime check do we need to emit to guard the vector version of this loop. Let's say A and B are pointers that get passed in through a function. We can't necessarily prove that they don't overlap. What are the runtime checks that we actually have to do? This one's a pretty easy one, right? We just look at the range of A, right? Where the first element that we access is A sub 0, the last one's A sub 999. Similarly for B, and all you need to do is make sure that, if this is A sub 0, and this is this is A sub 0 and this is A sub 999. You just need to make sure that either the bottom thing is bigger than B or the top thing is less than B, just to figure out that those things don't actually overlap. So that's the range of accesses of A and B. That's the runtime check that we actually would emit. What about this one? So I've changed it just a little bit. A sub I equals B sub I plus 1 times 2. This one's slightly more interesting, right? The range of A goes from 0 to 999. B doesn't go from 0 to 999. It goes from B sub 1 to B sub 1000. If we emit the runtime check that compares A sub 0 through A sub 999 to B sub 0 through B sub 999, we're actually generating wrong code. It's possible that they overlap on that last element where you're accessing B sub 1000. In this case, we have to this is the runtime check that we have to emit. Right, that plus 1 inside of B has changed the range of accesses of B that we have to check against. All right, next. What's the range here? Right, the range of A is pretty easy. It still goes from 0 to 999. But what does B go to? Right, with the first element, the lowest access of B is right when I is 0, that's B sub 1. And the highest is when I is 1000 and B is, the thing that we're accessing is 1000 plus 5. Which is actually wrong. That should be 1004. That's good? That's not good. The maximum value of I is 999. Yeah. No. Well, actually, you know what? Yeah, I put the question mark. So what about this one? Right, what are the range of accesses of B if you've got I plus X inside one of the array references? Any thoughts? Is X signed? So that's funny, but let's go with yes. Is X a reference? No, let's just say X is a scalar value. You pass it into the function, and it's just an integer. It's just assigned int 32. All right, what's the range of B? The answer is it depends, right? It depends if X is less than 1 or if X is greater than 1. If X is minus 1000, right, it's a little strange that you're accessing B sub I, minus 1000. But, right, what if X is 0? Right, then you're accessing B, the first element, the lowest element is going to be B sub 0, and the highest is going to be B sub 1000. But what if X is 20? Right, it changes the range. So if you really wanted to emit the runtime check for this, you actually have to find what the minimum value of X and 1 is. You also have to figure out what the maximum value of X and 1 is. Things get really interesting here. We don't do this in the compiler right now. We do, I think, all of the other cases. I was thinking about what we would need to emit for this. And actually, you need to do min and max to make sure you get the right ranges. This is where things get real fun. What about this? Right, so I've changed two things in here. One, it's now B sub I multiplied by I. But I've also changed the loop bounds, right? I goes from some lower bound up until I goes to some upper bound. This is, I think this stuff is really interesting. Right, you know that if you treated the step inside the square brackets, right? The address thing that you're using for B, right? It's just the quadratic that hits with a root at 0 when I is equal to 0. But right, what if the lower bound and upper bound are both negative? Things get interesting in that case. What if they're positive? It's a little weird. Like, what does the runtime check actually need to be here? And maybe you don't even need to check a range. Maybe all you really need to do is check that A sub 0 is less than some value and that the lower bound is positive. That's kind of weird. I think that stuff's kind of cool. I just thought it was interesting. Right? These are the things that we think about when we're emitting runtime checks. It's not just a straightforward, hey, does this array overlap with this array? There's much more interesting things that we can do. So that was the fun part of the talk. I had fun. I hope you guys had fun. Okay, so let's take some questions. All right, this guy had his hand up for a while. Go ahead, sir. Do we have mics around, or?
Yes, we do.
Just wake Charles up a little bit.
Where is it?
looking on your example with basic class and hierarchy of virtual function and so on and so on. So definitely just based on of hierarchy of classes, we may say that we have 3 options for function call. So do you have in your optimizer options to emit if
Yes.
checks without profile information? Because it can be done just by static analysis of the code.
Yes, so that's absolutely right. So we do that optimization to some extent. So we do not speculative devirtualization, but we do actual C++ devirtualization in a certain set of circumstances. We have a lot more work to do on it. If you write your code and then never end up using C, if the base class, or if the derived class C is never used inside anywhere of your program, we are going to insert those if checks without needing profile accounts. Absolutely do that. Similarly, if A is the only class that you actually use, we're just going to change every reference from any function inside of base just to A. But we know there's a lot of room for improvement there. Things get really interesting when you think about it in terms of compiling a big piece of code with static libraries. So let's say you've got some static library that shares a header file with whatever you're compiling against. How do you know that the static library hasn't created one of those base types? That's called type invasion analysis, and we have some of that. We just need to make it better. But yes, thank you for that question.
How about letting us have some pragmas to give you hints about it? Because I'm fine if the code crashes if I lie to you, but I'd like to be able to tell you this array is memory aligned on 32 bits, so you can use aligned loads, so on.
Okay, I want to spend a little bit of time answering this question. I'm a very long-winded person, and I think this question deserves a long-winded answer. So it's more than just pragmas. Let's take restrict. So restrict means if I've got int star restrict A. Oh, thank you, Ian, who works. Sorry to interrupt. Ian, who works with me on the optimizer team. He just told me what the value of m was in that loop. M is 10.
Thanks, Ian.
Okay, sorry to get back to your question. Now, restrict. So int star restrict A. We treat that what does restrict mean? So everyone's on the same page. Restrict A means my pointer A points at something, and nothing else points at that same thing. So if you're looking at that runtime check thing, right? If we need to check that A could possibly overlap with B and A is marked as restrict, well, the user just told us nothing could possibly overlap. So we do consume restrict in that particular case if you need to get rid of runtime checks. And restrict is a neat thing if you really chose to go down this path and we couldn't vectorize this loop because it needed runtime checks and the runtime checks were too costly or something. You could throw restrict on that. We're not going to emit the runtime checks. We'll vectorize that loop. I don't like that for several reasons. One, restrict is, what is restrict? Right, it's a keyword. It gets colored differently in my IDE when I type it. Is it a directive? Is it a pragma? Is it a hint? What is it? I know what restrict is. It's a loaded gun, right? That you take it and it immediately is pointed at your foot, right? Well, what if you get it wrong? And what if you get it right now, but 5 years from now, someone's modifying any other part of the code, and all of a sudden, there really is overlap now, and we can't do it, right? It's more interesting not just with vectorization, but in terms of automatic parallelization, where we could take a single loop and spread it across 40 cores, right? Then where pointer overlap just by one iteration can actually make a huge difference. That could not make a huge difference. Your code will be wrong. I really don't like restrict. I much prefer doing it in the compiler. So we do have interprocedural restrict analysis or interprocedural alias analysis where we gather what everything could possibly point to and what could alias with everything else. So we do get some of that information. Again, we know that particular part of the code also needs to be improved. Again, it's for the same reasons that the type devirtualization needs to be improved. But in some circumstances, restrict and those pragmas are going to be fine, but I can't in good conscience tell people to use them. Sorry. Find someone else, they'll probably tell you differently.
I have a question sort of similar.
than a pointer. Yeah, there we go. If you use a vector rather than a C array, then does that make it easier for the compiler to say, well, I see this vector is being declared or being created or whatever. I know the two vectors that are independently created and aren't a reference to another one or whatever cannot possibly overlap by definition of the way they're created. Therefore, that makes your job easier in terms of being able to do the parallelization. Is that true or not, or does it not matter?
So most of what you said I completely agree with. The one key part in there is how the vectors are created. The compiler has to see how the vectors are created, just as if the compiler needs to know how the C arrays are created. We know if the C arrays are created by just assigning from some global array or multiple global arrays that we know don't overlap. We don't need to do the runtime checks. That's part of that interprocedural alias analysis. And if you use a std vector, or if you just use stack arrays, or if you use global arrays, we'll figure that out, absolutely. But it doesn't matter if you use a vector or not.
Okay, so it's not, you can do the same analysis in either case. I was concerned that since vectors and since arrays decay into pointers when you pass them into a function, that therefore you lose information. That with a vector, you can tell how big it is, so you can say, oh, I know this can't overlap even if I don't. You see what I'm saying? Since you get more information, does that help you or does it not matter?
It might seem like we get more information, we don't get more information.
Okay.
Yeah. It really looks the same to the back end. Now, that is interesting because where I think the optimizer needs to start going is to consume a lot more information from the language and from the libraries. So I think the easiest example I can think of for this is all the different parallel for suggestions that are coming up of how to add some kind of natural parallelism to the standard library. The first versions of that are kind of come out, if we don't optimize those specially, then we're leaving a bunch of extra analysis on the floor. We're leaving a bunch of performance on the floor. The compiler optimizer really should know that when the user wrote std : parallel for instance, that should feed enough information to the optimizer to say, hey optimizer, every one of these loop iterations is actually independent. Make that information, do whatever you need to do with that information. And I think there's a lot of room for growth in that area in the optimizer right now, at least for Visual C++.
Two quick questions. For the runtime overlap checks, you were saying that they have to be completely disjoint. Is it acceptable for the vectorization instructions if the output does overlap, but like 4 slots or more behind the consumption? Is that okay? I'm thinking of like std copy, which, although it only works with single things, does permit overlap in one direction when you're not stomping over.
Yes, so one of the things I feared when I gave the example of data dependence is that I was making it seem a little bit too trivial. You're absolutely right. If you're vectorizing by 4 elements at a time and your arrays overlap by greater than 4, this stuff's really complicated. You have to
Well,
really
if you're gonna write something you're
okay.
going to consume, that's bad no matter how far. But in the reverse direction, I think you're okay. I assume you guys have already thought of this.
Yes, well,
Okay.
I think about this stuff like every night before I go to bed.
Awesome.
There's a whole branch of computer science devoted to just that problem of what array reference that we're writing to on one iteration is being read from a different iteration. It is a huge, huge, huge branch of optimization.
Second question. Programmers who optimize for size without PGO, are they horrible people or very horrible people?
So you have to profile. If you've profiled and then you've determined that I want to compile everything for size, I'm okay with that. Right? There are lots of components, take in Windows, that really the goal of them is to actually be as small as possible. That's totally okay. So if you've profiled, if you haven't profiled, you're just a terrible person to begin with, because you haven't profiled. I don't care if you're compiling with, you can compile without optimizations or whatever. That's not why you're a terrible person. But yeah, I think there's sort of the bigger outside part of that. If you know what your code's doing, yeah, sure, it's okay.
The vectorization instructions, do the speed depend? Does the speed depends on whether the operand aligned at 16 bits or not? It's 16 bytes.
Okay, so yeah, another long-winded answer. Take 100. So everything is microarchitecture independent. It's a little on the absurd side, but it's something that we have to live with. Take 128-bit code generation on x86 and x64, so SSE2 code generation, for instance. If you emit aligned versions of the instructions, your code will go a little bit faster on newer processors, and on older processors like prior Nehalem, so like before 2008, I think, they're going to run a lot faster, right? They're talking like 15% faster just from using the aligned version of instructions. With Haswell, that's not that big of a deal anymore. It's much, much more like 1 or 2%. The painful part is if you use an aligned instruction and your data is not actually aligned, your program will crash. It's not like it'll go to slow, but it will crash. The story is different with 256-bit vectorization on AVX and AVX2, where we don't have, I think Intel sort of got wind that we weren't using these aligned instructions because they make your program crash if we get it wrong. Then coming back to the pragma thing, right? What do you do if you've said it's really aligned, but it's not? So on AVX, they fixed that problem by the same instructions will take aligned versions and unaligned versions of your data, and the aligned ones will go faster.
I mean, there is a trick when you run in parallel aligned and unaligned reads, shuffle in registers, and then run. Anyway.
Yes, no, I know all about those tricks. I love those tricks. You get into major problems if you store some amount of AVX bits to memory and you load a subset of that. That actually harms chips these days. I can give an hour talk on just that one problem. I love that stuff. And that's something that can make code go a lot faster, scientific type code, especially where people think, hey, I'm storing a whole bunch of data in memory. Let's just use XMM types and XMM instructions. Do it 128 bits at a time. But if you're loading small components of that, if you're loading, the third byte out of every 8-byte chunk or 16-byte chunk that you're storing, there actually are severe performance penalties for that. So there's interesting, right? It's not as simple as just, oh, let's use this trick and shuffle things around. It's going to be okay. Yeah.
All right, I have a question. Are you done? No, I'm just kidding. Thank you, man.